So in this section we're going to be studying plane curves and parametric equations. Like our last section, this one is largely meant to be a review of what we could have learned in trigonometry, or MAT-111 at Greenville Tech. So I encourage you, if you find that any part of this is unfamiliar, now would be the time to look back through the textbook or look back through the notes and make sure you're up to date on how to do all these things. I don't have time to teach them from scratch in a very slow and thorough manner, but I do want to give you a little bit of an overview of the things we should know. And then I would say about 20 or 25% of this section will be adding on just a little bit to our discussion of parametric equations using some calculus. So the first thing I want to define is just what is a parametric equation. So basically it's going to be something where our coordinates, x and y, are each defined as a function in terms of some parameter that's normally going to be t. Okay, sometimes our parameter is like theta or a different letter, but most of the time it's just going to be in terms of t. So here's an example down here. X equals 24t, y equals negative 16t squared plus 64t. Okay, so a lot of times this is used to model the movement of an object, right? T might be representing time, and the x and y coordinates could just be the x and y position of that object over time. Okay, so the set of all the ordered pairs in a parametric function is called a plane curve. So basically, if you graphed that thing, the graph you end up with is the plane curve. So let's take a quick look at some basic examples of this. This is the one I was just referring to. So in this scenario, we have a cricket ball that's being hit into the air, and its position after t seconds is modeled by this equation. So they asked me to find the position of the ball right when it's hit, and its position 1 second after it's hit. So to find the position right when it's hit, I'm going to be doing t equals 0. So I'm going to take each of these equations and plug in 0 for t. Okay, and in both cases, x and y, I'm going to get 0. What that tells me is that immediately when the ball is hit, its position is 0, 0. Okay, the next question is what's the position 1 second after it's hit? Same thing, I'm just going to be plugging in 1. Okay, so you could even write this as x of 1 and y of 1. In other words, what happens when you plug in 1 to those equations? Okay, so I end up with 24 and 48, which tells me 1 second after I hit the ball, it's 24 feet forward and 48 feet in the air. So that's the answers to those questions. As kind of a follow-up, what if we actually wanted to graph the trajectory of the ball? So not just get some isolated points, but actually see what path that ball is tracing. Okay, well to do that, typically I'm just going to make a quick little table of values. Okay, I'm supposed to go from t equals 0 to t equals 4. So why don't I just choose some values from 0 to 4 and plug them in, and I'll see what happens to the x and y coordinates. So if I plug in 0 for x, we already found that, that's 0, 0. If I plug in 1 for x, we've already done that as well, that was 24, 48. If I plug in 2 for x, let's see, that would be 48. And let's see, the y equation would be 64. And I'm just going to keep plugging in each of these values. So if I plug in 3, let's see, I would have 72 and 48. And if I plug in 4, 96, 0. So I've got a little table of values. Now all I need to do is plot those points. Okay, so I'm setting up my axes. Starts at 0, 0. Then I've got 24, 48, 48, 64, 72, 48, and 96, 0. So there's the trajectory from t equals 0 to t equals 4. You'll notice this is a parabola. Now there's one more feature I need to add anytime I graph parametric equations, and that is the direction of my graph. These points don't all exist at once. At time equals 0, I'm right here. At time equals 1, I'm right there. So what I need to add is arrows showing which way I'm moving along that graph. I'm going from left to right. Because there's different parametric functions that could trace these same points, or in other words have that same plane curve, but go in the opposite direction. So we always need to add the direction that our graph is moving when we graph a parametric function. Okay, so the last thing I want to do is do a similar example and kind of compare and contrast. Okay, Okay, so we could also graph this function, 6t, comma, negative t squared plus 16t. What I want you to notice is I've already built out this table of values. It is the same x and y coordinates at these points, it's just at different t values. So it's kind of interesting that we can have two different parametric functions that trace over the same plane curve, that's the name for all those points, but that do it in different amounts of time. And in fact, we could even come up with a third function that does those same points and goes in the opposite direction. So I want to show you really quick just an illustration of how this works. Okay. So first I want to show you the first function we did. And you can access this interactive graph in your notes. Okay, so there it is. It's just going from 0, 0. It's just tracing along that parabola. What I want to show you next is, let's turn on the second graph. Okay, so we're going to reset it at 0. Okay, so it's going to hit those same points, but I want you to compare the speed. It's going way slower, right? So maybe this person's hitting a cricket ball like on the moon or something. Okay, and now let's show both of those together. Okay, so they're tracing those same points, they're just doing it at different rates. Okay, and like I said, we could even come up with a different parametric function that traces the same points in reverse, maybe at a third different speed. Okay, so parametric functions are very versatile. There's lots of different ways you can trace the same points, but they give you more information than just a regular function because they tell you at what parameter value, or in other words, generally what time we're going to hit each of those individual points.